Hello everyone, I am Dr. Naresh Kumar, Assistant Professor from the Department of Electrical and Electronics Engineering, Institute of Aeronautical Engineering, Hyderabad. Today we are going to have a discussion on question bank discussion on phase control rectifiers. So here we have total 20 questions. The first question in the phase control rectifier second module. So that is explain the operation of single phase full wave midpoint converter with R load with the help of circuit and output waveforms. So this is the circuit diagram of midpoint single phase full wave midpoint converter. So here we have two thyristors T1 and T2 are connected and one load. So that is R load is connected. So it is a center tap transformer. Here supply AC supply here we are giving. So here output voltage we are getting V0 output voltage we are getting across the load. Now here how it will operates first. So now here during positive off cycle. So now during positive off cycle A is positive with respect to the this N. So now here in this case the thyristor T1 is TH1 is conducting and now here so current is flowing from this A, TH, this R load and now this negative terminal. And next when thyristor this is negative. So now here this is when during negative half cycle. So thyristor T2 will conduct. So here current flows from. So here this plus R, TH and this minus. So that is here. Here TH1 will conduct. So it will TH1, so thyristor T1 will conduct at alpha. So during positive off cycle, so this supply, this is the supply we are giving at the input side. So this is the supply voltage we are giving at the input voltage, Vs supply voltage. And now here these are the firing pulses at during positive off cycle alpha and during negative off cycle also we are giving. This is for T1, TH1 and this is for TH2. And now give the firing pulse at alpha. So T1 the output voltage follows the supply voltage and now here this output voltage equals input voltage. This is the output voltage up to pi. And next after pi during negative half cycle. So this is the this output voltage equals minus of Vs. So that is it will follows the supply voltage opposite side. So that is the TH2 will conduct. Next this is the pi, this is the 2 pi. Here this is the case for current and this is the case for current. So from alpha to pi and from alpha to pi plus alpha to 2 pi and again 2 pi plus alpha. Now here what about the voltage across the TH1 and TH2? So now here voltage across the TH1 means here. So this is the case. Let me change the color over here. So now here this is the voltage across the TH1. So now this is the voltage across the TH1. So now this is the voltage across the TH1 and voltage across the TH2. Now here what about the output average output voltage waveform? So that equals it is conducting up to what angle? Here it will conduct up to what angle? So here output average output voltage from alpha to total time period is pi and it is conducting from alpha to pi and that is Vm sin omega t d omega t, that equals to Vm by pi 1 plus cos alpha. So this sin omega t integration is cos omega t minus cos omega t. So now this is the case for single phase full wave midpoint. So this is a midpoint. This is, we can call it as a M2 with R load. So with R load with the help of circuit diagram and waveforms. And next case here, second question, demonstrate the operation of single phase half wave R load with neat circuit diagram and necessary waveforms. So what about the circuit diagram? This is the circuit diagram. So now here Vs is the supply voltage, this is the R load, and this is the thyristor. We are giving the AC supply Vs equals to Vm sin omega t. So this is the sine wave. So this is the Vm is the maximum voltage. We are giving the supply to this SCR T1. So thyristor T. So now I am giving the firing pulse at alpha Ig. We are giving the Ig is greater than 0 at alpha, and next from the alpha to pi, from alpha to pi. So during this period, so the SCR is in from 0 to alpha. SCR T is in forward blocking mode. So even though it is a forward positive supply we are giving, but there is no gate pulse. So 0 to alpha. So it is in forward blocking mode. When it will be conduct from alpha to pi, SCR. So here Vs is positive. Here is also Vs is positive, and we are giving the gate current not equals to 0. Ig is not equals to 0. In that case, so output, it will follows the output voltage. So the output voltage equals to input voltage. Next, what about the current I naught equals to V naught by R. And next here this thyristor voltage equals to Vs minus V naught. So minus Vs minus V naught means here. So this is the case. So this one, and next remove this one, and next here it will follow the supply voltage up to pi plus 2 pi plus pi. So this is the supply voltage. This one is the gate pulses after 2 pi plus alpha. We are giving next pulse, and next this is the output voltage, and this is the output current, and this one is the thyristor voltage. So now here what about the, so this is the time period 2 pi, up to 2 pi it is conducting. So V naught average equals to 1 by 2 pi integral of alpha to pi only, it will conduct cos alpha, Vs means Vm sin omega t. So now if you simplify, Vm by 2 pi 1 plus cos alpha. What about this one? So now here I naught average value equals to 1 by Vm by 2 pi. So divided by this V naught average value equals to, that is R 1 plus cos alpha. This is the case. And next, what about the conduction angle? Conduction angle is from alpha to pi. So that is a conduction angle is a that is gamma of t, that is pi minus alpha. What about the extension angle? It is conducting up to pi value. So now here that extension angle is beta equals to pi. And next case here, peak inverse voltage is here. This is the peak inverse voltage, that is the Vm. So peak inverse voltage is that is the Vm. So now here circuit turn off time. What do you mean by circuit turn off time? Circuit turn off time means the time for which the SCR is in reverse bias. So now here that it is in up to pi duration, SCR is in reverse bias, but this is a forward conducting mode, forward blocking mode. Don't consider this one. This is the during this period only. So this is a pi, this is a 2 pi minus pi means that is a pi duration, SCR is in reverse blocking mode. So now here that equals to omega Tc equals to pi, 2 pi minus pi, that is pi. So Tc equals to circuit turn off time equals to omega, pi by omega. So this is important. Next question, second question, third question. Demonstrate the operation of single phase 2 pulse mid converter with R load and relevant waveforms. In the first question and this third question, both are same. Here there is a full wave. Here is also we have 2 pulses. Single phase 2 pulses midpoint converter. So with R load, this is the R load and relevant waveforms. already we discussed. From the alpha to pi, TH will conduct. From pi plus alpha to 2 pi, TH2 will conduct. So this is the input voltage waveform. Pulses we are giving alpha and pi plus alpha, TH1, and this is TH2, and load voltage, output voltage will follow the supply voltage from alpha to pi and pi plus alpha to 2 pi, and these are the current waveforms, and these are the thyristor voltage waveforms. Derive the expression for following performance factors for single phase fully controlled bridge converter, that is input power factor, next voltage ripple factor, active power and reactive power. So now here, so this is the case here, this is the here in the previous case, single phase fully controlled bridge rectifier. Here we have how many thyristor? T1, T2, T4 and T3. T1, T2, T3, T4. So total 4 thyristors. So first case here, T1 and T2 will conduct during from alpha to pi, and next T2 and T3 will conduct, and next here T3 and T4 will conduct. So this is the case for output voltage. Here total input power factor equals to 2 root 2 by pi cos alpha. So now here this is the input power factor, and next second one is the input power factor, and next second one is the, that means here here real power and reactive power and real power, P01, that equals to reactive power equals to Vi cos phi and active power equals to Vi sin phi. So this is a phi is the angle. So this cos phi is the fundamental displacement factor. From that you can calculate the sin phi. So here V into I means that is the RMS value of this one. And next here, interpret the operation of single phase 2 pulse midpoint converter with R load and derive the expression for average output voltage. So now here in the previously first and third questions are related to R load only, but here RL load. During this RL load, so now here after so at alpha, this is the pi duration, and this is the pi plus alpha, and this is the 2 pi, and this is the 2 pi plus alpha. What will happen from the alpha to pi, like R load, TH1 will conduct, and next it is a RL type of load, means inductor stores the energy in the form of magnetic field. It will delivers the power from the load to the source. So here from the alpha to pi, power is delivered from the source to the load, but from the pi to pi plus alpha, inductor delivers the power from the load to the source. So that is this is just because of inductance. So this duration during this pi to pi plus alpha, power is delivered from the load to the source. So this is the case. So it will follow the supply voltage. TH1 will conduct until this pi to pi plus alpha. So now here again pi plus alpha to 2 pi, TH2 will conduct. Again here this 2 pi to 2 pi plus alpha, this inductor delivers the power from the source to the load. So now here how we will calculate the average output voltage. So here thyristor TH1 is conducting up to from the alpha to pi plus alpha, V0 average equals to, what is the time duration here? Time period is a pi only, not 2 pi. So that is a pi duration. And now here this is the Vm sin omega t. So now here that equals to 1 by pi. So cos of So that is this is minus cos alpha. So now here pi plus alpha, this is the alpha. So now here what is the value that equals to 2 Vm by pi cos alpha. This is the average value of a single phase 2 pulse midpoint converter. So that with RL load, so that is a case RL load, and what are the derivation of average output voltage. And next case here, this is a V 2 Vm by pi cos alpha. So it is conducting from alpha to, so this is the pi 2 pi plus alpha. And now next case here, here what are the merits and demerits of single phase half wave converters over the full wave converters. So now here if you see the single phase half wave control rectifier, only some of the semiconductor devices are controlled. So other devices, diodes, which conducts current only in one direction. So in the half wave control rectifiers, there may be diodes. Okay, na? So now here diodes may be only current, they conduct only a current in only one direction. But typically, so the half wave control rectifiers used in the unidirectional power flow from the source to the load only, they will use. But here the control is limited to turning on thyristors while turn off the SCR. So that is the turn off process naturally handled by AC supply when the current goes to the zero. Here we are natural commutation we are using to turn off the SCR. So due to the limited controllability, the output voltage or output current waveforms may not as smooth as in the full wave controlled rectifiers. So now here common examples of half wave converters are here, half wave rectifiers and semi controlled rectifiers. Now if you see the full controlled rectifiers. So now here full controlled rectifier, in this these thyristors are controlled, allowing for both turn on and turn off control. But there is only turn on. So for turn off, there is a natural commutation we are using, that is because of AC supply. In the fully controlled rectifier, better controllability over the output voltage and output current waveforms. So that is compared to the half controlled rectifiers. So now they are what are the applications? They are used in the bidirectional flow control is required. So what are the bidirectional? So in the motor drives, HVDC, so systems we will use. So there is a only unidirectional power flow. So from the source to the load, but here from the load to the source and source to the load, that we will use. And here control over both turn on and turn off allows. So that is control strategies improve the power quality. And next here, what are the examples of this full control rectifiers, full wave rectifiers, full bridge inverters and choppers. And now next question, that is the seventh question. So examine the performance of dual converter. Here what do you mean by dual converter? In the dual converter we will use two converters. So here there is a two converters. One converter is a rectifier and another converter is a inverter. One is a rectifier and another converter is a inverter. So that both are connected to the load. So this is the dual converter. So the definition is a dual converter is an electronic circuit. It is having two circuits, two converters. One is a rectifier and other one is a inverter. So that is connected to the load. And what are the modes? Here we have two modes of the operations: non-circulating current mode and another one is the circulating current mode. So in this, at a time only one converter will operates. So only one rectifier or other one is the inverter. either rectifier will operates or inverter will operate. But here circulating mode, both converters. So both converters means rectifier and inverters both are operates simultaneously. So in the ideal dual converter, so it produces ripple free output voltage using diodes. There may be a diodes we will use here. So for unidirectional current while allowing flexibility in current direction. So what are the types of dual converters? Single phase dual converters and three phase dual converters. So now here for different types of AC supply convert. And next, what are the applications here? DC motor control, reversible DC needs, and industrial variable speed control, speed of DC drives. So now here I will explain what are circulating current mode and non-circulating current mode, and single phase dual converter and three phase dual converter. So that I will explain. So first here, what are the modes here? Two modes, non-circulating and circulating converter mode. In the non-circulating converter are only one converter, either rectifier or either inverter will operate. So there is no circulating current between the converters. So here only in one converter only current will flows, in another converter no current will flows. And during this converter operation, so now here alpha will operate from 0 to 90. So here alpha will operate from 0 to 90. So that is VDC and IDC both are positive. During converter 2, so this is rectifier and this one is an inverter. Firing circuit alpha 2 will be same, this range 0 to alpha. VDC and IDC both are in negative. In the circulating mode, so two circuits, so two converters will be operate on condition at the same time. So circulating converter, circulating current is present. So there may be a current from the rectifier to the inverter, inverter to the rectifier. So here alpha 1 plus alpha 2. So this is for rectifier and this is for the inverter. Alpha 1 plus alpha 2, that must be 180 degrees. This is most important. Converter 1 performs as a controlled rectifier. So this is the rectifier and that is 0 to 90, and inverter converter 2 is a that is inverter, so it will operates from 90 to 180. So now here in this the condition is VDC and IDC both are positive. So converter 1, that means rectifier performs as an inverter when the firing angle, so that is 90 to alpha, and converter 2, that is inverter, performs as a rectifier when that is 0 to, when that angle is 0 to 90 degrees. So in this case VDC and IDC both are in. So here sometimes it is a rectifier, it is a inverter. So when this angle is from 90 to 180, so it acts as a inverter. So when it is from 0 to 90, this angle is alpha 2 is, so it acts as a rectifier. So now this is the most important condition. And next here, what are the quadrants? So this is the 4 quadrant operation for dual converter. So I naught positive, I naught negative, V naught positive, V naught negative. In the first quadrant it acts as a rectifier, and in the third quadrant acts as a both are positive, both are negative, that is a rectifier, and if any one of the parameter is negative, that is a inverter. And next single phase, and this one is a 3 phase. So one is rectifier and another one is inverter, one is a rectifier and another one is a inverter. So this is the T1, T2, T3, T4, and next T4, T5, T6, T7. So these are the total 8 thyristors we will use here. 6 plus 6, 12 thyristors we will use. So now here this range is 0 to 90. Alpha 1 range is from the 90 to 180. So alpha 2 ranges, alpha 1 plus alpha 2, that must be 180 degrees. That we must know about this. This is three phase, this is single phase. What are the applications? So the direction and speed control of DC motor, and applicable whenever the reversible DC is required, and industrial variables speed DC drives. And next, eighth question, demonstrate the working principle of half-wave control rectifier with RL load. RL load we discussed in the previous question. What will happen? So R load, that is R load. So in the R load up to pi only, this SCR will conduct. So here this supply voltage we are giving. So now here from the alpha to pi, so SCR-T will conduct. From pi to pi plus alpha also, this SCR will conduct. That is just because of this inductance. RL is connected in series. RL is connected in series means here what will happen? This from alpha to pi plus alpha, this SCR will conduct. So here power is from alpha to pi, power is delivered from the source to the load, but here from the pi plus alpha to pi plus alpha, from the load to the inductor, just because it will deliver, it stores the energy in the form of magnetic field from the 0 to alpha. That energy after pi to pi plus alpha, inductor will deliver from the load to the source. So now here current will increases up to pi and again decreases to pi plus alpha. So now here current conduction is from alpha to pi plus alpha. This is the inverter thyristor voltage. So Vs minus V0 is the thyristor voltage. So now here it will conduct V0 average equals to 1 by 2 pi from alpha to pi plus alpha, 1 by pi. So that equals to 2 Vm by Vm cos alpha by pi, that is V0 average value. So this is the case for single phase half wave RL load. So now here, see for midpoint converter, so what is the formula when alpha equals to 0 here? So that is the formula, that equals 1 by pi alpha to pi Vm sin omega t. So that is Vm by pi alpha to pi sin omega t. So that is sin omega t integration is a minus cos omega t Vm by pi from the alpha to pi. So that is Vm by pi 1 plus cos alpha. So now here if you substitute is, that is Vm by pi 1 plus, so cos pi by 4 means here Vm by pi, so 1 plus 1 by root 2, that equals to Vm by pi root 2 plus 1 by root 2. So this is the equation, this is for alpha equals to 45 degrees. And next here derive the expression for average output voltage, and for single phase 2 pulse, that means full wave bridge rectifier. So is this one is first question same as, so same, that is it will conduct from the alpha to pi, again from the alpha pi plus alpha to 2 pi it will conduct. So from the alpha to pi Vm sin omega t, that is 1 by pi integral of alpha to pi. So Vs sin omega t supply voltage, Vs equals to Vm sin omega t, Vm by pi integral of alpha to pi sin omega t d omega t. So that equals to Vm by pi. So sin omega t integration is a minus cos omega t from alpha to pi. So that equals to Vm by pi 1 plus cos alpha. So now this is the case. Average output current equals to this voltage by R, means that is the current. And next 11th question is explain the operation of DL converter. So that is already we discussed. It is operated in two modes. So one is non-circulating current mode and circulating current. First, in the non-circulating current mode, only one thyristor, in this. So this is a circuit diagram of DL converter. So in this one, we have two converters. One converter is a rectifier and another converter is a another converter is an inverter. So rectifier alpha 1 range is 0 to 90 and alpha 2 range is from 90 to 180 degrees. 90 to 180 degrees. Alpha 1 plus alpha 2 equals to 180 degrees. So now here first I will explain uh, non-circulating current means only one converter will operates and other converter will not be operated. So that is non-circulate current will flow in the only one circuit, either in rectifier or in the inverter. In the circulating mode, so here current will flow from one converter to the another converter. So now here one is acts as a rectifier and another is acts as the inverter. So alpha 1 range and alpha 2 range, alpha 1 plus alpha 2 is 180. Sometimes so if alpha 1 is 90 to 180, so that case this converter 1 will act as a inverter in sometimes if it is 0 to 90. So now this converter 2 acts as a rectifier, so that we have already discussed. This is the case for 3-phase dual converter. These are the applications. So now here, so this already non-circulating current and circulating current we discussed. And next case here, single phase full wave converter with RL load, and RL load we already discussed. So that in the RL case, so here this, so TH1 and TH2 will conduct from the alpha to pi and pi plus alpha to 2 pi and 2 pi plus alpha. So to TH1 up to 2 pi for R load. When we connect the freewheeling diode, what will happen? What are the main advantages of freewheeling diode? There is no negative output voltage. So here it will freewheels the, so there is no negative output voltage. So now here there is a freewheeling diode. So this is, so there is no output voltage decreases. And next here, so when alpha will increases, so that input power factor will increases and input power factor will increases. So that is the main advantage. So now here this is the case. So this is the voltage waveform, this one is the current waveform. So it will this freewheeling diode freewheels this one. So it should not be negative. And next case, what about the output power? So it is conducting up to 1 by pi. So but that means 2 into 2 pi by pi, alpha to pi only, from the alpha to pi only, Vm sin omega t, Vm by pi 1 plus cos alpha. So that equals to Vm by pi, that is Vm by pi by R 1 plus cos alpha. Next, 13th question is illustrate the effect of source inductance on the performance of single phase full bridge inverter. So now here this is the case. So now here without source inductance. So now without source inductance I will explain first. So here without source inductance, so here T1, T2 will conduct, and next again. So like this, so your output you will get like this. But here just because of this inductance, source inductance, what will happen? So inductor does not allow sudden changes in currents. So if where there is a source, when there is a source side, there is an inductance. Inductor does not allow sudden changes in currents. So this IT current and this inductor current and T1, T2, this T1, T2 current and T3, T. So it will not increases suddenly, it will not decreases currently. Without a source inductance, so there may be suddenly increases, suddenly decreases. So immediately they will start. But here during this period, T1, T2, T3, T4, all thyristors will conduct at a time. Just because of the source inductance, it will not allow sudden changes in currents. So T1, T2 thyristors will not decreases from maximum value to the this positive to negative, and T3 and T4 will not increases immediately from the negative to the positive. So here there is no output voltage. All thyristors will conduct, all are short circuited, means that voltage is zero. This is important. So this angle from alpha to pi plus alpha, so from alpha to pi plus alpha, so that is pi plus alpha plus mu, so that is mu overlapping during this period. So T1, T2, T3, T4 thyristors conducting at a time. So that is the most important. And next here, single phase fully controlled bridge rectifier in the inverter mode. So when it will be operated in the inverter mode, when there is a inductance in the load side only. So now here this is the T1, T2, T3, T4 total thyristors, 4 thyristors. So when it will be operated in the inverter mode, so when there is a inductance in the load side, so that I will explain. So now here in this case, so first what will happen, so now from alpha is less than 90 and alpha is greater than 90. So if alpha is greater than 90, so if alpha is less than 90 from, so here T1, T3 will conduct. So now here this is the case. So this is the output voltage up to pi, so alpha, pi plus alpha, and again 2 pi plus alpha. So now here when it will be conduct, so if alpha is greater than 90, so it will trigger at, this is the 90 and this is 135, suppose 120. So now here this is the inverter mode, so this is the rectifier mode, and this one is the inverter mode. So now here, so from 0 to 90, that is the rectifier mode. From the 90 to 180, that is the inverter mode. So that is negative, and that V maximum is negative and V maximum is positive for the rectifier, and V maximum is a negative for the rectifier. So observe these waveforms. So that is a current waveform, that is, this one is a current waveform. Alpha is less than 90, alpha is greater than 90, supply voltage and supply currents. And rectifier mode, and less than 90 degrees case, input supply is rectified by the circuit average value of output voltage at the DC terminal from the 0 to 90. So now here power is delivered from the source to the load, but in case of inversion mode, power is delivered from the load to the source. That is important. That is regenerative braking mode of this one. Such operation is known as a regenerative mode in the inversion mode. So that is from alpha is greater than 90. So from 90 to 180, load voltage is negative, which means the power is delivered from the load to the source. Here these 2 points are source to the load, and here load to the source. And 15th question is, so with the help of circuit topology, voltage and current waveforms reflects with the help of input source impedance, means that is inductance, average value of output voltage in a fully controlled rectifier. So it will affect the average voltage, average value V0 because of the inductance. So there is no output voltage. V0 average will decreases, and this conduction angle will decreases. So now here this alpha is the overlap angle. So here all thyristors T1, T2, T3, T4 thyristors will conduct at a time. So that is the impact of source impedance on. So source impedance will decreases the average output voltage. And next here, what is a freewheeling diode? Freewheeling diode means here when you connect the freewheeling diode, when RL load is connected, and when you connect the freewheeling diode, so what will happen? So average value, output power will decrease. Output power will be positive, output power will be positive, and next input power factor will increases, and next efficiency will increases. These are the main advantages. So now here, just because of output voltage will never be negative, so and output power is also increases, input power factor increases, and next efficiency will increases. So now here, this is single phase half wave control rectifier. So if it is that is RL load to Vm by pi cos alpha, but it is if it is having, this is for RL load, but if it is RL with freewheeling diode, so now here that is Vm by pi 1 plus cos alpha, Vm by 2 pi 1 plus cos alpha, that is V naught average, and this is a V naught average. So now, just because of this one, input power factor, so output voltage will not be negative. So here it will come like this. So output voltage will not be negative, and current, continuous current, here continuous, another advantage is this is output voltage is always positive, there is no negative, and input power factor will increases, and next efficiency will increases, and fourth one is output voltage increases, and 51 is a continuous current is possible. Continuous current mode is possible. That are 5 advantages of freewheeling diode in the phase controlled rectifiers. So here already we have discussed that is circulating current mode. In the circulating current mode, 2 converters will operates at a time. So one is so on condition at the same time, so that is circulating current. So here alpha 1, so this is rectifier, this is alpha 1, and this one is alpha 2. Alpha 1 plus alpha 2 value always must be 180 degrees. So converter 1, it is, suppose it is a rectifier, and this is a inverter. So now here what will happen? What will happen if this value is always 0 to 90, and next here this is 90 to 180. If suppose this value is 90 to 180, so it acts as an inverter. If suppose converter 1 is 0 to 90 and converter 2 is 90 to 180, so VDC and IDC both are is positive. If suppose this inverter is 90 to 180 and 90, so if it is a 90 to 180, it acts as an inverter. If it is a 0 to 90, it acts as a rectifier. Explain the operation of non-circulating converter, means only one will convert. So rectifier, either rectifier or either inverter will conduct. So one is a rectifier and another one is a, both are from 0 to 90, from the 92. VDC and IDC are positive. So when 0 to, when first one is rectifier and both are is negative, when both are negative, only one converter will operates at a time. And next, with the neat circuit presentation and associated waveforms, explain the working principle of single phase fully controlled rectifier with RLE type of load. RLE type, one extra R resistor, inductor and one battery is connected to this SCR. So this is the output voltage waveform. And next here, this one is a output RLE type of load, means output current is always constant. And next here, this is the supply voltage. We are giving the pulses at T1, these two thyristors at this one, and next these two thyristors T2 and TH4 at pi plus alpha. So now here that current, this RLE type of load, so a highly inductive type of load. So here this is up to pi. So but here the minus this E means that is the output voltage. 2 pulse mid converter with RL type of load. So already we have discussed from the alpha to pi and pi plus alpha. So it will conduct from the alpha to pi plus alpha, that V naught average equals to 1 by pi integral of alpha to pi plus alpha Vm sin omega t. So that equals to 2 Vm by pi cos alpha, that we have seen here. That is the current waveform and this is the voltage waveform that already we have discussed. I hope all these questions are clear to you. If you still have any doubts in this lecture, you can comment in the comment section below. I will answer to your queries. Thank you very much to you all.
Like, share and subscribe. Hit the bell icon for more updates.